Thanks for attending, everyone. We're getting people filing in here. We always love hearing where everybody is tuning in from. So if you wouldn't mind sharing in the chat where you're joining us from, we had people from all over last time, so I'm curious to see who's in our audience today. You can just go ahead and open that chat button. Beth from Bandon, excellent. Seal Rock, I love Seal Rock. Albany, nice. Lincoln City, Houston, Texas, very cool.
Again, the person's
Yeah,
friend.
and Nebraska's back too. Thanks, Courtney. Waldport, Hillsborough, Albany, Garibaldi. I love seeing how people are spread so far, and everybody loves the Oregon coast, so we love to see that. Laura and Lou in Port Orchard, Washington, not too far away. Love it. Awesome. So we'll give Mike from Idaho. We'll give just another moment here for people to start settling in. If you were here last week, welcome back. If you weren't, thanks for joining us. A reminder for everybody that we have the question and answer feature here in this webinar. So if you have questions throughout Ed's talk, go ahead and put them in that question and answer box. The chat is easy to miss them in, so I want to make sure we're able to get them all answered. So if you put them in that question and answer box, we'll have time at the end to go through those, but don't let yourself forget. You can type them right in as you think of them. And then at the end, we'll go through all of those questions. And it looks like we're 6:02 right now, so I think it's time to get started. Go ahead, Ed.
Good evening, everyone. Thank you for joining us. If you're new to this series, this is a three-part series, as you can see on your screen. Last week we went into Oregon coastal geology pretty heavy. This week we're going to be looking at coastal beach dynamics, which will involve some geology and mostly focus on the oceanography. And next week we'll focus on the Columbia River Estuary. Okay, so tonight, coastal ocean and beaches. So first, let's have a look at the oceanography. This is the big picture. Gyres and currents. Gyres are big circular oceanographic features. You can see a number of gyres on the screen in front of you. Every major ocean basin has its own gyre. So looking at the Atlantic, you can see the North Atlantic subtropical gyre. On the left-hand side of that, you can see the Gulf Stream. The Gulf Stream pushes north, and that's what brings warm, moist air up to Europe. It's why palm trees grow outside of London. Whereas if you look at the same latitude to the west, you're over in Newfoundland, where there are no palm trees. So it's that Gulf Stream that keeps Europe warm and mild. The Canary Current is a return current going south there. That brings a cooler, drier weather along Spain there in Africa. And then the loop continues with the North Equatorial Current. Moving over into the Pacific, you can see we have a similar gyre. I will go into that in some detail. These gyres are primarily driven by winds. I will go into that in a few minutes. So the surface waters are responding to winds, and also the gyres are responding to the geography. So the water masses bang up against the continent and they change direction. And also the Coriolis effect is involved here. And I apologize that we just don't have time to get into a lot of the nitty-gritty, but something called the Coriolis effect is involved with these currents too. And once again, you see a major gyre in the Indian Ocean, in the South Atlantic Ocean, South Pacific Ocean. So the southern hemisphere have similar gyres. Like I said, what is driving the circulation patterns is largely wind. And you can see in the red and the green arrows that they are the winds, trade winds, and the prevailing westerlies is what is driving the North Atlantic gyre there. And moving over to the Pacific Ocean, Here we have our major gyres in the North Pacific. I'm going to focus on the North Pacific here. So you can see that we have the North Equatorial Current going from east to west, being driven by winds. The North Equatorial Current turns into the Kuroshio Current, and that turns into the North Pacific Current, which eventually turns into the California Current. And the California Current is what bathes the west coast of the United States. And because the current, those waters are coming from pretty far north, it's what keeps the north coast of the United States relatively cool and dry, as opposed to the east coast of the United States is bathed by the Gulf Stream, which is coming directly from the equator, which keeps the east coast relatively warm and humid. Okay, let's move in a little closer to the coast and have a look at coastal currents. This is a picture for Oregon and Washington, where the big blue arrow shows a major current bathing the west coast of the United States is the California Current. And that's just what we saw in this slide. The sea is the California Current coming down from north to south. What you didn't see on the previous slide was a Davidson current. And the Davidson current is a current that is driven by low pressure systems that occur off the west coast of the United States during the winter. And those currents, those low pressure systems blow from south to north and bring waters up the coast from the south. And so the Davidson current is really just a seasonal current that is inside of the California Current. Upwelling is a major oceanographic feature along our entire coast, California, Washington, and Oregon. And it is driven, what drives upwelling is offshore wind. So you have offshore wind pushing the waters offshore, and that creates space for upwelling. And what that does is that upwelling brings nutrient-rich, relatively cool waters up to the surface, and that's what makes the Oregon coast and even the California coast good fishing, because that upwelling is bringing nutrient-rich deep waters up to the surface, and that's just what the fish like. They like those nutrients. And I'm going to come back and we'll look at upwelling again a little later. But once again, a very predominant feature along our entire coast. We can't talk about West Coast oceanography without talking about El Niño. And you've probably all heard about El Niño. So these are normal conditions that I'm showing here. And what you see is with those green arrows up in the upper part of the picture, those green arrows are a high pressure system, and those winds, that high pressure system keeps warm waters over into the western part of the Pacific. And that's just what you see there. You see a warm blob of water around the equator sitting off the coast of Asia. And what happens is that warm body of water is allowed to flow eastward when the high pressure system breaks down. So occasionally that high pressure system breaks down, and that allows the warm waters to flow eastward, and that is what is called El Niño. And what it does is it brings humidity, it brings rain, it brings unstable atmospheric conditions to our west coast, and that's why all kinds of wild things climatically or weather-wise. That's why a lot of wild things happen on the west coast during El Niño. It's bringing this unstable air. It's bringing a lot of moisture. It's bringing rain. Often it'll bring strong winds, and that is El Niño. So once again, El Niño is the breakdown of that warm body of water that you see over in the western part of the Pacific, and it allows the warm water to come over and bathe the west coast. Okay, let's have a quick look at tides. You probably all have a warm, fuzzy feeling about tides. I'll go into it in a little detail here. So what you see here is you see the moon over to the right, and the moon has an attraction on the surface waters, and that attraction pulls surface waters to it, to the moon, and it also creates a bulge. So that pulling of the water toward the moon creates a bulge on the opposite side of the Earth. So we get essentially two high tides due to the pull of the moon. So we get a bulge toward the moon, and we get a bulge away from the moon. And what's driving our tides is the moon. And if you look at the top part of this picture, you might think, gee, the sun is so much bigger than the moon. Why does the moon have so much more of an impact? And once again, it's a gravitational attraction of the moon on our surface water that's causing these tides. So you might think that the sun being so much bigger would have a bigger pull. But if you look at the bottom part of the picture, you see what's happening. And I think that's to scale, approximately to scale. The sun is just so much further away, and the moon is so much closer. So if you see my cursor here, over on the left-hand side, you can see the tiny moon is so much closer to the Earth that it is driving, it is the primary cause of our tides, although the sun has somewhat of an effect. We have a monthly tidal cycle. We have spring tides and we have neap tides. Spring tides are when the full moon is when the moon and the sun are in line. You can see that in that top cartoon. So you have the pull of the sun, and then you have the pull of the moon, and the sun is just amplifying the lunar effect. So you have bigger tides. The opposite of that is a neap tide, where the sun and the moon are at right angles to the Earth. So you can see you have the moon pulling upward, you have the sun attraction to the right, and what that does is essentially that the sun dampens the lunar effect, so you have smaller tides. So once again, it's the moon that is primarily driving our tides. There are different tidal patterns depending on where you are on Earth. You can have a diurnal pattern where you have one high and one low tide per day. You have a semi-diurnal pattern where you have two highs and two lows per day, with the tidal range about the same. Then you have a mixed tide where you have two highs, two lows, but the tidal ranges are different, and that's most common. And that's what we have on the West Coast. And this is showing it pictorially. So that top picture is showing a diurnal pattern where you just have one high and one low per day. And where we see that is in the Gulf of Mexico. And I used to live along the Gulf Coast, and I used to surf along the Gulf Coast. It was really strange. You only had one high and one low tide per day. It takes a while to get used to. And the reason for that is that the tides are essentially, the high and the low tides are essentially a huge wave that is just oscillating around the Earth, being pulled by the moon. And that bulge, that tidal bulge, just can't completely make it into the Gulf of Mexico. And by the time it gets into the Gulf of Mexico, it's time for it to get out. So that's why the Gulf of Mexico, being a semi-enclosed basin, just has one high and one low per day. That middle cartoon is showing a semi-diurnal tidal pattern where you have two highs and two lows, two high tides and two low tides per day, but the amplitudes are approximately the same. So the high tides are similar in amplitude to the low tides. And most common is the bottom picture, the mixed tidal pattern, where you have two highs and two lows per day, but the amplitudes are different. And the arrow isn't showing that, but that's what we have on the West Coast of the United States. We have a mixed tidal pattern. And the reason for the mixed tidal pattern versus a semi-diurnal tidal pattern just has to do with the geometry of the continents. So again, this big wave is sloshing around the surface of the earth, and just based on the geometry, the configuration of the continents, sometimes the amplitudes are the same, and sometimes they're different. Longshore drift. If you live along the Oregon coast or the California coast, if you live along any coast, you are a witness to longshore drift. What longshore drift is, it's a movement of sand, it's a movement of sediment along the beach being pushed by the predominant longshore current. And that's what this little cartoon is showing. You see the waves coming in at an angle from left to right. And as those waves bang into the beach, it's moving sediment. So the sand grains have a net movement of left to right in the direction of longshore current. And that movement of sand grains is called longshore drift. This is a stark example of one of the effects of longshore drift. This is the coast of Maryland. And what's happened here, just back over time, is that one of these mansions, and I don't know which one, these are all big houses. One of those houses built one of those groins that you see out on the beach, because that person wanted to grow their beach. So they put a groin there, and the person knew that groin would trap sand and it would increase the size of their beach. Well, over time, more houses moved in, and everybody got the same idea, and everybody built groins. And the net effect here is that you can see is an asymmetrical beach where the predominant longshore drift is from right to left, and you can see the buildup of the sand on the right side of those groins, because those groins are trapping the sand. So the net effect of this is not good, because there's going to be somebody down beach to the left there that's getting gypped out of a lot of sand. So these groins are not a good idea. They disrupt the natural flow of sand along a beach, and there's just all kinds of issues with these kinds of structures. Well, I'll come back to that in a few minutes. This is the mouth of the Columbia River. Unfortunately, north is to the left here, and Astoria is up here where my cursor is. And over here to the left is Washington. So that's the Columbia River. That's the mouth of the Columbia River we're looking at here. To the left is Washington. To the right is Oregon. And if you think about this for about 2 seconds, you could tell the direction of predominant longshore drift along the Oregon coast. And the predominant longshore drift is from north to south, or in this picture, from left to right. And why that is so obvious is that you can see the big sand buildup on the north side of the Columbia River jetty, whereas the right side, or the south side, is being starved of sand. And that beach that you're seeing there in Oregon on the right-hand side is the Fort Stevens Beach, and that is eroding at the rate of 1 to 2 feet per year. Now, sea level rise is a little bit involved here, but largely the reason is that the Fort Stevens Beach is being starved for sand because of the North Columbia River jetty. On the other hand, the Washington side is being built out, and you can, if you're familiar with the area, you can get up on the cliff and look out and see how much land has been built up on the north side of the jetty. So good for Washington, but Oregon is losing sand, at least this part of the beach. Rip currents, just a couple words about rip currents. You've probably all heard about rip currents. Rip currents are common along the Oregon coast, and every summer, invariably, some little kid gets sucked, or even, actually, I shouldn't say just little kids, even adults are sucked out into deeper water, some of them drowned due to rip currents. And how they work is that you can see to the left and the right of that arrow, you can see regular waves coming in. Now, when that water comes in, it has to have an outlet, and due to just the beach geometry, there'll be some conduit on the beach that will allow the return of that water back out to the open ocean. And that water, so the water coming in finds that conduit and returns to the ocean by way of a rip current. And if you get caught in one, it's not a good thing. And you can even tell by the surface of the water, you can tell that the rip current going out has a different superficial expression than the waves coming in. If you're a surfer, that would be a good way to get out into the waves. You just hop on your board and you ride out on the rip current that takes you out, and then you paddle over and you get into the wave to ride. If you are trapped in a rip current, you do not try to swim directly in. You'd have to be a really strong swimmer to swim against that current. So you would swim either to the left or to the right, get away from the rip current, and then just ride the wave in. Okay, let's shift gears here a little bit and let's talk about beaches. What I'm showing here are two very different kinds of beaches. We have a typical looking beach on the east coast of the United States. It's the Outer Banks of North Carolina. The Outer Banks are a series of barrier islands off the coast of North Carolina. And to the right is a photo of the Central Oregon coast. Now, the question I ask is, what's the difference in these two beaches? What causes the obvious difference in these two beaches? One beach to the left, the Outer Banks, is a relatively straight beach, nice sandy beaches, no rocks, whereas on the right, we see a very different looking beach. And the difference we talked about last week. The difference has to do with tectonics. So this is a cartoon that I showed last week showing subduction that occurs off the Oregon coast. The subduction causes uplift, causes mountain building. Also, we talked about microcontinents banging into the Oregon coast, causing the Oregon coast to look like what we see on the right. So what's driving the difference in these two beaches is tectonics. Summer beaches along the Oregon, actually along all coasts, there's a stark difference between a summer beach and a winter beach. Generally during the summer, the storms are milder, there's light wave activity, and the beaches are generally wider, as opposed to the winter beach, where there's a heavier wave activity. The sediment is moved offshore, and one of the most noticeable features are the formations of offshore bars, and you can see that in the bottom cartoon, where the sand is eroded off the beach and moved offshore, and they form offshore bars. If you fish, you are well aware of this phenomenon. So, excuse me, this is a photo of the Fort Stevens Beach during the summer, and I contrast that with the winter. Beaches look very different. What's happening there is in the winter beach is that we have winter storms, and those winter storms cause a very noticeable erosion, whereas during the summer, the dunes build out. So there's more deposition occurring during the summer, whereas erosion during the winter. And this isn't just Oregon, but it's maybe more starkly apparent in Oregon because of the greater topography that we have along our beaches. Because of beach erosion, there is a constant effort to stabilize beaches, because beach stabilization is a real issue. And just knowing the erosion rate on this beach, this house isn't going to be there. I know where this is on the North Central Oregon coast. That house probably has 20 years to go before it's going to fall into the ocean. Similarly here, you can see the one corner of the house is already hanging over air there. This house doesn't have too much longer to go either. And this is the East Coast. That has a real issue too. So there is a big push to try to stabilize beaches in order to save real estate. However, there are some real problems with beach stabilization. One, it's temporary. Two, you're robbing sand from neighboring areas. You're interrupting the flow, the natural flow of sand along the beaches. So before going any further with this, I want to talk to you briefly about the four major types of stabilization. What are the four methods that we have come up with to try to stabilize our beaches? So the first are groins. We've already seen these. Like I said, not a good idea. It might help locally, but in the long run, net erosion is going to outpace net deposition, and the whole coastline is going to suffer due to these groins. Jetties are typically found at the mouths of rivers in order to try to keep them open, and that's exactly the reason for the Columbia River jetties, to keep the mouth of the river open for shipping. But once again, as you can see, it interrupts the flow of the natural flow of sand along the beach, and one side benefits and the other side suffers. So jetties, just like groins, are short-term solutions for an unsolvable problem. The Army Corps of Engineers has to continuously come and dredge the mouth of the river to keep it open, or else it would just fill in with sediment. I want to diverge here a little bit and tell you a little story about Bay Ocean. Bay Ocean is a little town that used to exist along the Oregon coast. It was founded in 1906, and it was gloriously called the Atlantic City of the West Coast for about 10 or 15 years. So here's an aerial photo of where Bay Ocean is. At the top, you can see Garibaldi. Garibaldi is a little town not far from Astoria, and to the south is Cape Meares, and that stretch of beach between Garibaldi and Cape Meares there along the coast is Bay Ocean. This is a bathymetric map showing the Bay Ocean spit. So it's showing that same spit that we see, that same stretch of land that we see in this picture. It's showing it here prior to the construction of the jetty, and you can see that the spit pretty much coincides with the north-south trend of the beach. So developers came and they built their little town of Bay Ocean. So back in 1914, it had a population of 2,000, and this is out on the spit. To the left there, you see some highlands. Those highlands are still there. And the Bay Ocean had the famous natatorium built on Bay Ocean. It was a pretty upscale development, and this natatorium had a heated pool with a wave machine in it. So it was a pretty groovy place to hang out. Unfortunately for Bay Ocean, they built a jetty up there at the mouth of the river, and just like on the Columbia River Estuary, that jetty blocked the natural movement of sand. And you can see the buildup of sand up in this area. But what it did was it starved Bay Ocean for sand, and Bay Ocean eroded. It migrated back. And once again, so here's a look at the bay, at the spit prior to jetty construction. And this is after jetty construction. So you can see a large movement of that whole area to the east after the construction of the jetty. And after the construction of the jetty, it wasn't soon. It didn't take too long for Bay Ocean to fall into the ocean. And here's a natatorium in 1926, 10 years or so after it was built. So another way to protect beaches is with breakwaters. And this is a classic one in Long Beach, California. You can see the breakwater to the left. It was built as a protection for the harbor. There are some big yachts tied up there, and the people of Long Beach, California wanted protection for their yachts. So they built the breakwater, but you can see what happened. If you look at the beach, you look at the beach profile, you can see that sand has built out there because it's protected, so the storms aren't hitting that part of the beach anymore. But to the north and south, there's erosion. So to the north of the breakwater, it's being eroded. To the south of the breakwater, it's being eroded, and it's a real issue in Long Beach due to the loss of beach north and south of the breakwater. So not a good solution. Good for the yachts, but not good for the people who are living north and south of it. And one of my favorite stories is from Seabright, New Jersey. I was born not far from here. And this exclusive little community of Seabright was losing its beach just due to natural erosion. So they wanted to preserve their beach. So they built a seawall. And it cost like $10 zillion. It's 6 or 8 miles long. And it's that big pile of rocks that you can see behind the breaking waves. And between the seawall and those houses, the condos that you can see there, there's a road. So what it did was, sure enough, it protected the road and the condos, but only temporarily. That wall interrupted the natural flow of sand so that now the beach has been eroded. All the sand, that beach that used to be there, is essentially gone. This is during the winter, during a storm where there is no beach, but even during the summer, the beach is probably 20 or 30 feet wide. That's all. So it was a real fiasco. It cost big bucks to build. And in the long run, it has increased erosion, not decreased erosion. Once again, it interrupted the natural flow of sand so that Seabright is being robbed of its sand due to the increased wave activity on the beach. So another example of a not good solution to preserving a beach. Okay, so what are some alternatives to hard stabilization? And there are 3 major alternatives. Relocation is one. I see this on the Oregon coast. People are picking up their houses and moving them away from the beach. Good idea, except very expensive, as you can imagine. Beach replenishment is another option, and construction restrictions, and I will go over all 3 of those alternatives. So the first is relocation, and my favorite example is back again on East Coast, where you can see on the picture of the right, the famous Cape Hatteras Lighthouse. And I used to surf at that groin that you can see right next to the lighthouse. Good waves there. And I know for a fact that during storms, waves would come up and come right up to the lighthouse. So it became a real issue. And it was such a tourist attraction that they just felt they had to come up with a solution. So they moved it. And that's what you see on the left there. They laid train tracks starting there at the former location of the lighthouse. And they lifted the lighthouse up. And they put the lighthouse on a flatbed, essentially a flatbed train, and they moved it almost 3,000 feet. And it's safe now. It's going to be a few decades before the sea level will rise to the point that the lighthouse is now. So they saved their tourist attraction, and what did it say? $12 million to move this thing, and it'll last for 50 years or so. So relocation is an option, but again, expensive. Another option is beach nourishment. And what you're seeing here in the picture is a dredge ship offshore, and it has a big siphon on the bottom of it, and it's sucking up sand, and it's shooting the sand inland. and you can see the pipe there. And then you can see the sand that's being dredged being shot out onto the beach. I actually saw this process in motion. It is really something to see, and there are some big issues with it. The first is it is an ecologic disaster. Those dredgers know where the sandbars are, so that ship is sitting over a sandbar, and it is removing the sandbar, which is a environment for a lot of little creatures. So there's all kinds of benthic creatures, bottom dwelling creatures that are living on that sandbar that are now being sucked up and shot onto the beach. And if you stand there and watch it, you can see clams and crabs and other benthic critters being shot out onto the beach. Secondly, it's temporary. It's very temporary. After a couple of hurricanes and just sea level rise, this process will have to be done again at the same spot. And it's terrifically expensive, as you can imagine. And a few years ago, it was proposed on the Oregon coast to do just this in order to shore up the beaches in front of sections of 101 that are becoming precariously close to the cliffs. And they're afraid that with continued erosion, 101 is going to fall into the ocean. So beach nourishment was proposed, and Oregon Shores, the group that I'm with, spoke up very loudly about this process, mostly because it's temporary and it's an ecologic disaster and it's really expensive. So again, a short-term solution to a long-term problem. Oregon's goal 18 is a statewide, essentially a law that limits the excuse me, that limits the placement of beachfront protective structures like riprap and seawalls. It's limiting those hard structures to just those areas that were developed prior to 1977. So any building along the coast after 1977 cannot have hard structures. However, people get around it. There are exceptions. They get attorneys. They fight this law, and every once in a while they win, but every once in a while they lose too. So Oregon recognized this problem, that hard structures are not a good solution, and Oregon has spoken up, and good for Oregon for doing this. Okay, I want to shift gears again here and have a look at rocky habitats. And Oregon is unique. There are few places in the world that have the intertidal rocky habitat environments that Oregon has. Washington has them. California has some, but Oregon has some really good ones. So here's the first test question for the night. Where would you find greater species diversity, on land or in the ocean? And if you said land, you get 2 points. Very good. Yeah, what's going on here? Why there's more species diversity on land compared to the oceans is that the oceans are a much more stable environment. And that's what this little cartoon is showing here. The picture to the left is showing the open ocean, where the temperature range is something like 34 degrees in the global open ocean. Whereas if you move closer to land, you can see that the temperature range is about 42 degrees. And when you get on land, the temperature range is something like close to 150 degrees. So because of that broad temperature range, the ocean environment is much more stable, whereas the land environment has a lot more ecologic niches in order for species to fill. And it's not just temperature. There's elevation effects. There are rain effects. There are deserts. There are soils. Soils are homes to lots of creatures. So there's just a lot more ecologic diversity on land. So you have a lot greater species diversity than in the open ocean. Okay, question number 2. Where would you find greater species diversity? On the Outer Banks of North Carolina or Central Oregon. And I hope by now you get what's going on here. A lot more species diversity on the Oregon coast, where there are a lot more ecologic niches for species to fill. And just a demonstration of that, here you see a lot of potential rocky habitats for all kinds of critters to live that you don't see on the East Coast. And same thing here. Okay, let's have a little a closer look at our intertidal environment. Here we see a typical rocky habitat on the Oregon coast. I took this, I think, on Short Sands Beach, maybe. Anyway, what you see here is an intertidal area. And when I say intertidal, the tide, it's intermediate tide here. So the tide, I forget if it's coming in or going out, but at one point the tide was higher. And so a lot of those, a lot of the plants and the animals that you see exposed now on those rocks used to be underwater. And as the tide keeps going out, the plants and animals that are now underwater are also going to be exposed. So the creatures that are living here and the plants and the animals that are living here have to be adaptable to being exposed to air and being underwater. The water here, when this picture was taken, was probably something like 46 degrees, 48 degrees, something like that. And now the plants and animals that were living in an environment of 46 or 48 degrees are now exposed to the sun. If it's during the summer, it could be 80 degrees. If the tide goes out, and those tidal pools that we see there, that water that we see remains, it's salt water, but on a summer day or any day that there's enough sun, that water will become hypersaline. The water will evaporate, leaving behind salts. So those waters could go from open ocean values of 32 parts per mil, something like that, to very high salinity values. And if there's a heavy rain, the salt water could be flushed out and that water could become fresh. So those organisms have to put up with being underwater, being exposed to air, living in fresh water, living in regular marine water, and then a hypersaline and a freshwater too. They also have to put up with predators. There are stars crawling around, sea stars crawling around that would like to eat a lot of these creatures. There are fish that would like to eat them. So they have to have mechanisms to protect themselves from predators. Storms come by, huge waves could be breaking on these rocks, so they have to be tied to the rocks in such a way that they're not broken off routinely. And every now and then a log will come bouncing along the coast, banging into these plants and animals, so they have to be tied really fast to the underlying rock structure. I would argue that there is no environment on Earth that subjects animals and plants to such diversity. I just don't know of any environment that has so many changes that the indigenous creatures have to put up with such drastic changes in their environment. And not only do they have to put up with drastic changes in the environment, but the species diversity is some of the highest in the world too. There are, you can see here just part of the list of the animals and plants that live in the rocky habitat environment. So a very unique environment in all the world. Littoral cells. Littoral cells are something that are also unique to the Oregon coast. I'm sure they exist elsewhere, but certainly not on the East Coast and not as well developed in California or in Washington. Excuse me. What you're seeing here are the littoral cells that have developed on the north coast of Oregon. So up north, we're looking at the South Jetty, and we're going as far south as Pacific City. And we'll just take the first littoral cell. So between the South Jetty and Tillamook Head, we see a littoral cell. And that is the beach that exists between the South Jetty and Tillamook Head. And these littoral cells exist all the way down the coast. So between Tillamook Head and Cape Falcon, we have another littoral cell from Cape Falcon south to Cape Meares, and so forth. And what happens here is that I already showed you that the predominant longshore drift along our coast is from north to south. And that longshore drift is carrying sediment with it. And that sediment, that longshore drift, is bypassing those littoral cells. So if you look at the sediments between the South Jetty and Tillamook Head and compare those sediments to the sediments found between Tillamook Head and Cape Falcon, they're different. What's happening is that for that northern cell, that cell is pretty much dominated by sediments coming out of the Columbia River. So a lot of fine-grained silts and clays and muds. Whereas the cell between Tillamook Head and Cape Falcon is predominated by the couple of rivers that feed into that area. And those rivers are coming from the coastal range. So there are a lot more heavy minerals found in the sediments than you would find up to the north. So more plagioclase, more pyroxene, hornblende, more heavier minerals, indicative of a source to the mountains, to the coastal range, to the east. And the same thing between Cape Falcon and Cape Meares. That area is the sediments are dominated by the local influx of sediments coming down the rivers. So really a unique geologic and oceanographic setting with these littoral cells. A littoral, by the way, means coastal. So I could have just said North Coast coastal cells, but they're called littoral cells. Tsunamis. We can't discuss the Oregon coast without looking a little bit at tsunamis. So what causes a tsunami? Tectonics. So here we see on the left side of that little cartoon, we see some movement along a fault block. That movement can be significant. And what it does is it pushes up the water, creating a wave. And that wave is propagated in all directions. And that's what's shown in the picture of the globe up above. So where the fault movement occurred, it's creating a tsunami propagating out in all directions. So back down to the bottom part of the picture. So the tsunami creates the wave. That wave moves inland. And eventually the wave starts feeling bottom. It starts feeling the bottom in shallower water. It slows up. The wave slows up. And it also raises up. And eventually, as it continues closer to shore, it breaks. Just a quick picture here of some of the major tsunamis since 1990. The big one here that you see was Indonesia. That's Indonesia back in 2004, where there were over 300,000 deaths. The height of the tsunami was over 100 feet. Back in 2011, the big one in Japan killed almost 20,000 people. The wave height was about 130 feet, and so on and so forth. If you look at the top part of the picture, you can see that tsunamis pretty much only occur on the West Coast because of the subduction that occurs along the plate margins, along the margin of the Pacific Plate, that we don't see in the Atlantic Ocean. And if you remember from last week, the Atlantic Ocean has a mid-Atlantic ridge running down the middle of it. So there's new plate material being created there, and there is no subduction. And this is a picture of the Indonesian tsunami. And what happened here was that when a tsunami occurs, it's just almost by chance what's going to hit the beach first, a peak or a trough. If a trough hits the beach first, what happens? The water is all sucked out. The beach water is sucked out, and all of a sudden the beach can be hundreds of meters wide. And if you're on the beach bathing, you might say, "Oh, look, the beach has grown. Let's run out and see what's out there." And that's exactly what these people did. So the first part of the wave train that hit the Indonesian coast was a trough. The water was sucked out. The people were lured out because it looked interesting, but the trough was followed by a peak, and now you see the peak roaring in, partly responsible for all the deaths that we saw in Indonesia. And this is what the peak looked like. There is evidence, there's geologic evidence of the last Oregon tsunami that occurred back in 1700. And this is some work we did in Young's Bay, where this was on the side of the bay where we did some digging there, and we exposed a couple meters of sediment there, and you can see the layers, you can see the banding in those sediments, and the one that we are pointing the white stick at is the last one that occurred back in 1700. And the evidence that we saw for that tsunami were deep water microfossils that were up in Young's Bay. Deep water fossils would never occur in Young's Bay, but due to the tsunami, they were washed in. If you're a paleontologist or a marine biologist, what we found were planktic foraminifera. And then we dated the other events. Marine debris. The marine debris is a real issue along all coasts in the entire world. The vast majority of the marine debris are plastics. No surprise there. Most of the marine debris comes from land, and the plastics are not readily biodegradable. And a couple of years ago, there was a paper put out by NOAA suggesting that plastics will last approximately 500 years in the oceans before they break down. Something that I want to spend a couple minutes on is this phenomena called the Eastern Pacific garbage patch. So there we see the North Pacific gyre that we talked about earlier, and due to winds and due to the way that the Coriolis effect works, that I know we haven't gone into, but anyway, a quiet place of the North Pacific is over there where the Eastern Pacific garbage patch is. And what's happened is that a lot of the garbage that ends up in the north, that gets into the North Pacific, is shunted into that area that they've called the Eastern Pacific garbage patch, and it is accumulating there big time. It is maybe almost 1,000 miles, or almost 1,000 miles in diameter there, and there's all kinds of rubbish occurring in that garbage patch. It's a real mess. There are attempts to clean this up, and companies and governments are coming up with all kinds of techniques for scooping this stuff up. The problem is that this garbage patch has become a breeding ground for animals and plants. So life is living and breeding on these floating plastic rafts. There are jellies, there are turtles, albatross are nesting there. So there is an ethical dilemma here of what to do about it. It's essentially a new marine ecosystem. So can we ethically go out and clean it up? We're going to be killing a lot of organisms. So it's a real issue, and I don't know what the solution is, but I wanted to make you aware of the problem. You've probably seen pictures like this, horrible pictures. There's a seal with some kind of plastic wrapped around its neck. There's some plastic attached to a gull's beak. You've probably seen seabirds cut open and their innards are filled with plastic. It is a real issue that needs to be addressed in a serious way. Nurdles, plastic nurdles are all over. These things are pretty small. If you go on a beach and pick up a handful of sand and look at the sand with a hand lens, you can see these little nurdles. These nurdles are the building blocks of bigger plastic structures. So I'm not an expert in plastics, but from what I understand, all plastics originate from these nurdles. So these nurdles are the building blocks for the bigger plastic structures that we use all the time. And these things are ubiquitous. I even understand that they are found in people. There's something called the NOAA Marine Debris Program that I've been involved in on Fort Stevens Beach here on the North Coast. I've been doing this since 2018. I have a group of people that volunteer with me, and these are the results from 2018 to present. And what you see here, no surprise, 84% of the stuff we find are plastics. Almost half of it are hard plastic fragments that we don't know what they are, but we can tell it's hard plastic. There's a lot of foam, bottles, food wrappers, film, fragments, plastic ropes, et cetera, et cetera, et cetera. Some other stuff we find is processed wood, cloth, rubber, and just other stuff. So if this at all appeals to you to get involved with helping clean our beach and doing science, this is NOAA's Marine Debris Program. You're welcome to join us. And actually, you're welcome to get involved with Oregon Shores any way you want. We have a number of citizen science projects going on, and you can find out more about us at oregonshores.org. Offshore wind and upwelling, you're probably familiar with the recent bidding of leases, offshore wind leases along the Oregon coast on the south coast. There were 5 bidders, 4 of them bailed out. There's only 1 bidder left, and they all billed because of the opposition, so much opposition against having the offshore wind platforms built out there. And there are a lot of legitimate concerns, digging trenches along the beach, how it would disrupt the beach. There has to be infrastructure in order for these cables to tie in with electrical outlets on land. There are issues with fish. There are issues with birds. There are issues with whales. I'm confident, though, that the environmental groups involved will address a lot of these issues. For instance, making the windmills noisier. Another issue is that these are floating platforms. The water is so deep out there. These are floating platforms, and a lot of people are upset, accusing the offshore wind people of using the Oregon coast as a laboratory for these relatively new floating platforms. But they're not new. They're found in Europe. One thing I do want to address here, and that is early on, I was attending meetings, and the fishing industry was saying that these offshore wind platforms, floating windshore platforms, were going to decimate the fishing industry because the platforms would shut down upwelling. And as an oceanographer, my gut feeling was that was ridiculous. There is no way that those cables, so the offshore wind platforms, are going to be tethered to the ocean floor by means of cables. And just intuitively, I couldn't see how these cables were going to shut down this broad oceanographic process of upwelling. I didn't have any proof, but sure enough, last year There's a paper at a professional conference at the Hatfield Marine Science Institute entitled Potential Effects of Large-Scale Floating Offshore Wind Farms on Coastal Upwelling. These guys are physical oceanographers. They did a lot of numerical modeling. And what they found, if anything, coastal upwelling would be enhanced, not shut down due to these wind farms. So I just have to had to say that to lay that issue to rest. There's a lot of potential energy that can come from the ocean, aside from the wind farms, waves, lots of energy associated with waves, mostly with large storms, but also just due to tides. A lot of wave energy is generated just from natural tides. There are building issues, building the plants close to shore. There will be some interference with sediment movement and life, but it's a relatively simple operation. The west coast of Scotland uses it. Simply, you can see on the right there, the wave comes in, there's an oscillating, the water column oscillates, turning a turbine. That turbine is tied to a generator. And it's a relatively simple contraption. It just hasn't been embraced by the United States at this point. There's also a lot of energy that we could harness from currents, undersea currents. Issues here: expensive, difficult to maintain, some hazard to boating, but it's something that certainly could use some looking into. And with that, that's all I have to say. Are there any questions?
There are a few questions.
Good.
The first one that we've gotten in here is, this is really interesting. Did the temporary mini moon have any effect on tides?
I'm sorry, did the temporary?
Mini moon?
I don't know.
I know, right? I hadn't thought about that. I never heard of a mini moon prior to this, but I don't know much
Question.
about it either.
Yeah, good question. You know, I could probably do better if I was an atmospheric scientist. So all I can say is I don't know. Good question,
Yeah,
though.
very good question.
Yes.
Um, and then we have from Diana, more of a comment, great insight. Another option, this is when we were talking about revetments. Another option is nature-based shoreline stabilization
Yes.
revetments. In Cannon
Yes.
Beach, we have 5 lots protected by sand-filled burritos planted with hooker willows. A couple have lasted over 2 decades. OPRD has no records of repairs for 4 of these revetments.
And I knew about that, and I should have included it. Thank you. Yes, and congratulations, Cannon Beach, for doing that.
Yeah, that's
And
awesome. We love.
Cannon Beach is in the only place, East Coast. There are some
Okay,
local areas are doing that too. Yep, good point.
that's great. I'm glad to hear about that
Yes.
successful endeavor over here. We've got another one. With climate change increasing the strength of north winds, how will that affect longshore drift and coastal erosion?
Yeah, good question. I don't know if north winds are necessarily going to increase. Um, yeah, that's kind of a big picture question. If north winds increase, erosion will also increase. But there is so much at play here. I'm not sure if you can point to north winds necessarily increasing. In
Yeah.
fact, it's possible that, and this is getting kind of involved here, but it's possible that due to the shutdown of downwelling of North Atlantic water, downwelling in
Mhm.
the North Atlantic, it could actually throw the whole Pacific gyre out of whack.
Oh,
So I'm
wow.
not sure that gyre that we had talked about. I'm
Mhm.
not sure if that gyre is going to keep looking the same as it does today with continued global warming. I'm not sure. Good question,
Yeah.
but yeah, we're not sure.
Yeah, lots of things I guess we're going to be finding out about in the next few decades.
Yeah.
Gwen also asked, I thought you were going to tell us about the Columbia River basalt flows.
Ah, I, next lecture.
Oh, another
Yes,
cliffhanger.
you're right. I did say come back. I did say come back for this talk, but it's really the next talk when I'm talking about the Columbia River Estuary that I'm going to talk about the Columbia River basalt. So I'm sorry for misleading you there, but you're going to have to come back next week.
Oh, that was the trick, but Gwen, we're glad you're on it.
I'm
Uh,
sorry about that.
so they will be covered next week, though.
Yes, yes.
And then we have a comment from Dave in the chat saying that the mini moon is so small that it would have little effect on tides, basically no measurable effect on tides. So,
And that's my gut feeling too.
yeah, very interesting mini moon. All right. Anybody else have any questions? Feel free to drop them in the Q&A or the chat here. We'll give another moment or so for anybody that might be typing. All right. It looks like that might be it for the night. If you have any questions, you can email us or make sure you tune in next week and we will talk about the basalt flows and many other things. Anything else you'd like to say, Ed?
No, that's all. Thank you for your attention and thanks for the comments and questions.
Yeah. Thanks, everyone. I hope you have a good night and we will see you next week.